All right, let's try another one. This time, we're going to find the particular antiderivative little f for the function f double prime of x equal to 12x squared plus 6x minus 4. And so here we have a second derivative, and we're going to work backwards twice. Now, we know with finding particular antiderivatives, when we looked at the first example, what were we doing? We had a f prime, and we were working backwards once. So we had one initial condition here. Now, in this example, we're working backwards from the second derivative. So we need two initial conditions. So each time we do the derivative, we lose a little bit information. So if we've done the derivative 2 times, well, there's 2 pieces of information that we need. So let's see how this is going to work. All right, so if we're given f double prime, we're going to have to work backwards twice. So the first step is we need to find f prime. That's the first step. And so we can set up our equation. F prime of x is equal to the integral of f double prime of x dx. So the integration cancels off one of the derivatives here in our second derivative. That's the way you want to think of it. So let's fill in our second derivative. It's 12x squared plus 6x minus 4. We're going to do the antiderivative of that function. So when we look at this, there's just 3 terms here that we need to integrate. So we just go term by term. So let's start with our first term here, this 12x squared. We're going to integrate that. So the 12 is a constant multiple, so it can just stay out front. And then our variable here is x. So our variable is going to stay x. We add 1 to the exponent, so that takes us up to 3. And we're just doing power rule. So we take that new exponent, flip it, put it in front. So 1/3 x cubed. So we get 12 times 1/3 x cubed. And that's the antiderivative for this first term. All right. Now we'll move on to the second term here. We're going to integrate 6x. So we just move on. 6 is a constant multiple, so it can just stay in front. And we're going to worry about finding the antiderivative of x. So our variable is x. We add 1 to the exponent, so there's kind of like a hidden exponent of 1 here. So when we add 1, it bumps us up to 2. We take that new exponent, flip it, put it in front. We get a 1/2. And there we go. We have our antiderivative for that second term. And then we just go on to our third term. We want to find the antiderivative of 4. And so whenever we have a constant all by itself, normally with derivatives, that constant all by itself gets differentiates to 0. But with integration, we actually build it back up. So this is not going to be 0. When we integrate this is actually going to become 4x. And we have subtraction there, so we're going to have subtraction here. And plus c at the end. And there we go. We have our first derivative f prime. And if we simplify this, 12 times 1/3 is 4. 6 times 1/2 is 3. And then minus 4x plus c. So there's our nice f prime of x. We still have this constant c here that we'll have to figure out. But if we look at our initial conditions here, we have 2 of them. And both of our initial conditions are for the original function f. So at this point, we don't have any information to help us find c. Sometimes with initial conditions, you might have one initial condition for the original function, and then you might have another initial condition for f prime. So if you had the initial condition for f prime here, you could use that to figure out c. But our 2 conditions here relate to the original function f. So we have to wait. All right, so now we have our first derivative. So now we want to go one more and find the original function f. So we're going to find our original function. and we're going to integrate our first derivative. So again, the integral and the derivative, they get canceled off. They cancel each other off. And we get back our original function, and then we'll just have some more constants to deal with. All right, so let's fill in 4x cubed plus 3x squared minus 4x plus c. That's the function we're going to integrate. So now there's 4 terms here that we need to deal with. All right, so let's start with our first term, 4x cubed. When we integrate this, the 4 is a constant multiple. We do the power rule on x cubed, and when we do that, we get x to the power 4. So, when we do it, we'd have 4 times 1 over 4, and that leaves us with x to the 4th. And then we go to our second term here. We're going to get the antiderivative for the second term. And when we do that, we get x cubed. Again, I'm not showing all the work I did in the last step because, once we start getting the hang of the power rule, you're probably just going right from here and getting the answer. Then we do our third term, and it's minus, so we end up with minus 2x squared. And then here, this last term is a constant, c. So we know we're going to have, when we integrate just a constant all by itself, even though we don't know what c is at this point, we're going to find it. But when we integrate a constant all by itself, we get c times x, or whatever that constant is, times x. Now that's a pretty good antiderivative, but whenever we integrate, we always have to throw on an arbitrary constant at the end. So seeing how we're already using c for something, we'll just go to the next letter and we'll use plus d. Or if we wanted to, we could say like c1 and c2. That's another option. But we'll use c and d. All right, so you can see here that it's important to remember our constant. Because when we actually get the antiderivative, now there's this term here that actually has a variable with it, c times x. So this is actually a pretty important part of our function here. It's a variable part of our function. So going from f double prime to f prime, we got a constant. And then going from f prime to f, we ended up with c times x, and then plus another constant. All right. So now we have our function just about. There's just these 2 constants that we need to figure out, and that's where the initial conditions come in. So the next step here is to find c and d using these 2 initial conditions. So how are we going to do that? Well, we know, let's start with the first one here, f of 0 is equal to 4. So that's the first initial condition we have. And let's see what happens when we actually plug 0 into what we have. So this is what we have for f of x. Let's plug 0 in and see what we get. So if I plug 0 in here, I get 0. If I plug 0 in here, I get 0. If I plug 0 in here, 0. 0 into this one, I get 0. And so all I'm left with is d. So when I plug 0 into what I actually have, into this entire thing, I end up with just d. And so we want these 2 values to be the same. This is what we want, and this is what we have. We want them to be the same. So we just set these 2 equal to each other and solve. So we get d, or 4 is equal to d. So we know what d is. Sometimes there might be more work here, but what we're doing is we're just solving. We're setting them equal and solve. All right, so that's not too bad. Now let's see the other initial condition. So this is f of 1 equal to 1. So this is what we want. and we're going to compare that to what we actually have. So let's actually plug 1 into our function. So when I plug 1 in, I'm going to end up with a 1 here, a 1 here, a -2 here, C, and then we actually know what D is. So when we plug in, we get 1 plus 1 minus 2 plus C plus D. And when we look at this, 1 plus 1 minus 2, those just cancel out. And so we have C plus D. And we actually know what D is, so let's use that. Well, let's actually just set these equal. So what we have, f of 1 is equal to C plus D. And what we want that to be, we want it equal to this. We want it equal to 1. So 1 is going to be equal to C plus D. And use what you know about D. So at this point, you might have like 2 equations, and you just want to solve these 2 equations simultaneously. So we were able to actually do this one okay and solve this first one without referring to the second equation. But sometimes you might have to use one or both of the equations to kind of help solve the other one. So sometimes we don't always get this lucky where we actually can figure out from the first equation what one of the constants is. Sometimes you might get an equation involving both C and D here, an equation involving both C and D here, and then you kind of have to solve one of the equations first and then plug it in over here. So that's what we can do here is we know what D is. We know D is equal to 4. So replacing that, we get 1 is equal to C plus 4, and then solving for C gives us C is equal to -3. All right, so now we have all the information. We know our original function just about. Here we go. It's x to the 4th plus x cubed minus 2x squared plus cx plus d. And we've figured out d, and we've figured out c. So the very last step then is to just answer the question, put it all together. So our original function, little f of x, is x to the 4th plus x cubed minus 2x squared. And instead of c times x, we actually know c is -3. So let's fill that in. So we're going to have minus 3x. And then instead of d, we actually know what d is. D is equal to 4, so plus 4. And so there we go. We have our particular antiderivative here. We've actually figured out all those arbitrary constants. All right, so you can see we were given the second derivative, and so we had to integrate twice. One integral to undo each of those derivatives. And then each time we undo a derivative, we need an initial condition then to figure out the constant. So we had 2 initial conditions here, and we were able to kind of recover our function completely. This is the particular antiderivative. And like we said before, in that last example, here we were only kind of going backward from the first derivative, so we only had to integrate once. And because we were only undoing one derivative, we only needed one initial condition here to figure out our constants. All right, so that's really the idea. What we're going to see next is how we can use integration to help us with problems involving position functions, velocity, and acceleration for objects moving in a straight line. So we'll see you there.